Alright, this is the next lesson for Physics 11. What we're going to be doing is continuing our work with dynamics and looking at forces and how forces are being applied to different objects. And in this lesson, we're going to look at connected objects. Okay, so in this one, we're looking more at multiple masses that are connected together, and how do we deal with the forces that are being applied to multiple masses that are connected either by a string or just being pushed against each other, and then the force that kind of adds into the force between those objects. How does that play in with what we've been dealing with, our net force equals mass times acceleration. So that's what we're going to take a look at now. It might be a little bit long, this one, but I want to make sure we cover as many examples as we can. All right. Okay. So like I said, what we're going to be looking at is, again, it's still dynamics. It's still looking at Newton's law. And if you remember when we did Newton's laws, just talking about what they were, number 1, 2, and 3, Newton's third law says that for every action, there's an equal and opposite reaction. Okay? So we had talked about this in terms of normal force, right? When you have an object resting on a surface, you've got the force of gravity pulling down, but you also have this normal force kind of pushing up against it. Okay? This also applies to objects that are connected, right, such as joined by a rope, or like tractor trailers or other types of trains, right? Things that there's multiple masses connected with each other, right? So again, you've got, one is pulling one in one direction, but that same mass is kind of pulling it backwards as well, right? And there's that equal and opposite force, okay? So even if you think of something as simple as just walking across the floor, right? You are pushing on the floor, but the floor is also exerting a force back on you as well, but in the opposite direction. Okay, and this is essentially Newton's third law, right? Because if the floor wasn't pushing back on you, you would just sink completely into it. Okay, but the floor pushes back on you, which allows you to kind of keep on moving. All right. So even in, like I said, with connected objects, you can think about it in terms of tractor trailers, right? So you've got 3 essentially masses here. You've got the truck and the 2 trailers. Okay, and the truck obviously has a net force as it moves forward, right? It's not in not all the forces are balanced, right? We are ultimately moving, right? But you also have to remember here, so yes, this part's really pulling the truck forward, but you also have forces acting in between the 2 trailers themselves, as well as in between the truck and the first trailer as well, okay? There's forces that are existing in between those different masses, right? And then, not to mention, you've also got force of friction that could potentially be pulling back here as well, right? So a lot of times these are like forces of tension in the hitch, or if it was a cable, like force of tension in a cable, right? Or if they're pushed right against each other, we might just call it a contact force, which is what leads us to the next slide. Right, so when we talk about a contact force, it's a force that acts as a point of contact between 2 objects. And again, it's still that F is equal to ma, knowing the mass and the acceleration at which these objects are being pushed together, essentially, right, when they come into contact with each other. All right, so again, when we're trying to find that contact force or that force of tension that's happening in a system that has multiple masses, okay, again, we're still using our same formulas of F net is equal to ma, okay, but we have to be very careful when we're looking at the masses. If we're looking at the mass of a system, right, so if we were looking at what's the acceleration of this entire system, well, we need to think of all of the masses that are involved, okay, and then the overall applied force and maybe a force of friction. And what happens is that any contact force happening here, 1 might be pushing against 2, but 2 would be pushing against 1 in the exact same thing. So in the overall system, those things would cancel each other out, and we wouldn't be able to solve for them. Same thing with here with 2 pushing against 3 and 3 pushing back to 2. So what you would end up doing is, figuring out maybe the acceleration of the entire system, right, using your F equals ma, right, using all 3 of the masses. But then when you go to try and find that contact force or the force of tension in between, 2 specific masses, right, or in a particular cable, you're not going to look at the system as a whole, but instead just a specific mass, right, or just a specific specific contact force, right? So let's say if we were looking at something here, right, we don't need to worry about number 3 anymore, okay? The other way to think about it is the way that the slide's recommended here, whereas the value of m in your F equals ma when trying to find that contact force is the sum of all the masses behind the point where the contact takes place, right? So in this particular diagram, if if we're dealing with the contact force between 1 and 2, well, really we're dealing with these two masses here, right, times acceleration. And same thing with the contact forces between 2 and 3, we're just dealing with mass number 3. Okay, so again, it'll make a lot more sense as we go through the examples. Okay, so things that we still need to remember going into this, right? Yes, this is a new lesson, but it's still, you know, building off of everything that we've done still so far, right? So remember that if we are needing to find a value of acceleration, it's the change in velocity, or Vf minus Vi, divided by the change in time. Remember that your F net of an entire system, right, or F net of any kind of scenario is equal to the mass times acceleration, right? Remember, this is the sum of all the forces acting on an object, right, or acting on a system. Your force of friction here is your coefficient of friction multiplied by your normal force. You remember your force of gravity is equal to your mass times the gravity of typically Earth, right, unless otherwise stated. And remember that in anything moving, bless me, anything moving like horizontally, right, your force of gravity and your normal force will end up being equal, right, unless we're dealing with something, you know, a little bit different where something's just being suspended, which we'll get to later, or if it's being pushed up against a wall, right, obviously that would be a little bit different, right, but anything that's just on a flat horizontal surface, right, your normal force is just directly opposite your force of gravity, so they're the same values. Okay, so let's get into some practice problems to show kind of what we deal with here. So in this first one, you've got a tractor trailer pulling 2 trailers. It starts from rest and accelerates to a speed of 16.2 kilometers per hour in 15 seconds, and it's on a straight, level stretch of highway. Okay, the mass of the truck itself is 5,450 kilograms. The mass of the first trailer, we'll call it trailer A, is 31,500 kilograms, and the mass of the end trailer B is 19,600 kilograms. Our first question is, what magnitude of force must be generated in order to accelerate the entire vehicle if we're ignoring friction in this case? So let's take a look at how we would solve that. Okay, so again, with any type of physics question, we really do need to start off by listing the values that we know and what we're trying to find, right? So as we went through that question, we knew that this tractor trailer was starting from rest, so we knew that the initial velocity was 0 meters per second. We knew that it was accelerating to a speed of 16.2 kilometers per hour, which we can then convert into meters per second by dividing by 3.6 and getting a value of 4.5 meters per second. We know that that change in velocity happened over a period of 15 seconds. And we have 3 different masses, right? We have the mass of the actual truck itself at 5,450 kilograms. We have the mass of the first trailer at 3,500 kilograms. And we have the mass of the second trailer at 19,600 kilograms. Okay? Now, if we're just right now being asked for what force is going to move the entire system, right, the entire truck itself, well, what you have is, you know, your mass here that's being moved is a combination of all 3 of those, right? Your overall mass is the mass of the truck plus the mass of the first trailer plus the mass of the second trailer. And that is all being moved in a positive direction, which we're being asked to find, right? Right, this force applied, okay, ignoring friction, and, you know, again, it wouldn't really matter here because you'd have the force of gravity pulling down, but the normal force would be equal here, and our net force is only our force applied here, okay? So, going to figure this out, right, our applied force is equal to mass times acceleration. Well, we're moving the entire truck, so what we need to use for m here is the sum of all 3 of these masses. So our applied force is the mass here, which is the 5,450 plus 31.5 plus 19.6, and adding all those up, we get a value of 56,550 kilograms, right? And then we need to multiply by the acceleration of the entire system, the truck and the 2 trailers. And, you know, if the truck moves at this acceleration, so do the trailers being pulled behind it. And remember that acceleration can be found by Vf minus Vi divided by our change in time. So our acceleration is that 4.5 meters per second minus 0 meters per second divided by 15 seconds, which ends up giving us a value of 0.3. So our applied force to move this, force is equal to mass times acceleration, 56,550 kilograms, multiplied by, so this is 0.3 meters per second squared, okay, and then we multiply those two values together and get an answer of 16,965 newtons. However, based on the original question, the least number of digits here was the 15 with the sig figs, so we only get 2 sig figs, so this would end up being 1.7. So really it's like 1.7 times 10 to the 1, 2, 3, 4, okay, newtons. And that's the applied force necessary to move that entire system of truck and 2 trailers from rest to that speed of 4.5 meters per second in a 15-second time period, okay? All right, let's see what part B was there. Okay, so what was the force of tension in the hitch between the 2 trailers? Okay, so we take a look at that. I'm just going to erase the board. All right, so in this case, right, if we just think about in the first one we were thinking about the system, right, which was just one truck being moved along, right? Now we need to talk about forces within the system itself, right? So what you have is you've got your truck at the front, which is connected to your first trailer, which is connected to your second trailer, okay? Now we've got the applied force, right, that's happening here, right? And then what would have happened was you'd have these kind of force of tension in between the truck and the first one. But the question we were asked wasn't about that, but what was the tension within the hitch between these 2 forces here? Right, between those 2 masses, right, that's where the hitch is going to be between the 2 trailers, right, the mass of A and the mass of B. Right? Now, in the overall scheme of things, these would have canceled each other out so that we didn't need to worry about them in the overall system like we did in Part A. However, we do need it for this particular problem, right? Now, so what you have to do is you have to look at a single mass on its own, okay? So, obviously, this is part of mass A, but it's also a force acting on mass B. Choose the one that's going to be easier. Okay, so yes, you could do it with mass A, but the thing is that there's other unknowns when it comes to mass A because there's some sort of force connecting it to the truck as well, which we don't have really any information about. However, if we kind of just zoom in here on just mass B, because we've ignored friction, well, all that's happening to this, right, is that force of tension, right? If we eliminate the other things that cancel itself out, right, all that's happening is that force of tension in between the 2. So our force of tension is our basic, mass times acceleration. Okay, we know the mass of trailer B. It's that 19,600 kilograms. And because this mass is still part of the overall system, its acceleration that we found in Part A is still applicable here using that 0.3 meters per second squared. Okay? And then we can just calculate what that gives us. And it's a value of 5,880 newtons, but again, we need 2 sig figs, so we would use 5.9 times 10 cubed newtons. All right? So when we're doing this, right, you got to think about things as like the system as a whole, right? What are the sum of the forces acting on the system as a whole versus what's the sum of the forces acting on a specific mass? Okay, and we'll keep doing that in these sample problems to kind of get you used to that. All right, so these are just your solutions again to that. They're typed out. All right, so let's look at sample problem number 2. Okay, so in this case, we have a force of 6.4 newtons pulls horizontally on a 1.5 kilogram block that is connected by a string to a similar block with a mass of 0.93 kilograms, right? Similar meaning similar material, meaning the coefficient of friction would be the same. Okay, if the coefficient of friction between the blocks in the table is 0.16, determine the acceleration of the blocks and then the force of tension in the string. Okay, so if we take a look at this one, right? So again, if we were trying to like draw that kind of free body diagram here, what you have is you've got your first mass, right, connected to your second mass here, right? And what was happening was that there was an applied force acting in that direction, right, based on the diagram that we saw. And then you've got tension in a string, right? And like I said, you've got tension pulling this way and tension pulling this way. And in the overall scheme of things, they are going to cancel out, right? So that's your force of tension, and that's your force of tension. But the other thing that's happening here is we've got force of friction pulling back here, as well as force of friction pulling back on this one as well. Okay? So that's kind of what's all happening in that. But if we want to just think about the system, right? So that's what's happening in all the individual sections. If we just want to think about the whole thing moving as one coherent thing, well, your free body diagram kind of changes, where you just have a single mass, right, which is the combination of both of them, right, the mass of the entire thing moving, and the entire thing is being pulled with that applied force, with some friction being applied to it as well, right? So if we're going to go trying to find the acceleration here, right, we need to know our values. So the mass of the first block was 1.5 kilograms. The mass of the second block was 0.93 kilograms. Our coefficient of friction was 0.16, and we've been asked to find what is the acceleration of the system. So in the system, right, what's our net forces, right? So we've got our F net is equal to mass times acceleration. Well, in this case, your applied force is being pulled this way, and your force of friction would be going against it. So your F net would be your applied force minus your force of friction. Again, it's not moving vertically, so whatever force of gravity is being applied is going to equal and balance out with the normal force here, okay? And that's going to equal our mass, and the mass of the system is the sum of both blocks multiplied by our acceleration that we're trying to find, right? Now, the applied force was given to us in the question, right? So that was another variable that we had, right, where our applied force was 6.4 newtons. So that can go in for F of A. Our force of friction, we would need to calculate using our equation, which was coefficient of static friction multiplied by normal force, right? And then we have our two masses that we can add, right? 1.5 plus 0.93 gives us a value of, and I don't think I ever actually wrote that down. Just kind of did it all on my calculator. So it was the 1.5 plus 0.93. So the sum of the two masses here ends up being 2.43 kilograms. And then again, that acceleration of the system is what we're trying to find. So now what's missing is this normal force, right? But normal force, we just talked about, is going to be equal to the force of gravity here because we're not moving in a vertical direction at all. So our applied force remains the same at 6.4 newtons. We have our coefficient of friction, which was 0.16. And our normal force will be equal to our force of gravity, which would be the masses, right, the sum of the masses, which was the 2.43, multiplied by our 9.81 meters per second squared, right, gravity, and all of that is equal to our 2.43 times acceleration. Okay, so we can do all this, 6.4 newtons minus the 0.16 times 2.43 times 9.81, right? So what that gives us is, okay, there's my applied force of 6.4 newtons. My force of friction is the 0.16 times 2.43 times 9.81, which is 3.814 newtons. That's all equal to the 2.43 kilograms multiplied by the acceleration. So I can just subtract these, right? 6.4 minus that 3.814, get a value of 2.568 newtons is equal to the 2.43 kilograms times acceleration. And then to get acceleration by itself, you divide both sides by 2.43. So you do the 2.568 divided by 2.43, and you get a value for acceleration of 1.064 meters per second squared is your acceleration of the system, right? However, we only get 2 sig figs here, so we would actually round this to 1.1 meters per second squared. Okay, so for that first part was what was the acceleration of the system, right? What was the acceleration of these blocks? Well, it's at 1.1 meters per second squared. The other part of the question was what was the force of tension in the rope? Now, if we go back to our diagram, the overall one here, you notice that the force of tensions in the rope just cancel each other out, so that we wouldn't be able to find it using net force acting on the entire system. However, if we choose one of the masses on its own and only look at the forces acting on that particular mass, well, that will allow us to find the force of tension in the rope. Okay, so again, you can choose either one, right? You can choose to look at what forces are acting on the first mass. Well, you've got this applied force acting here, and you've got the force of tension acting here, but you also have the force of friction acting in this direction as well. Or you can choose to look at the second mass, where what you have is the force of friction pulling it back, and the force of tension in the rope is what's pulling it forward, right? There isn't an applied force being applied to the second mass. That applied force kind of trickles in through the force of tension, okay? So I would typically go with the easier one. So in my opinion, dealing with mass 2 involves one less force to deal with, so why don't we just go with mass 2, okay? So if we just look at this scenario, right, again, our net force is equal to mass times acceleration. We know that the forces acting on this, right, the force of tension would be a positive force, right, because this is the direction of motion, and the force of friction is hindering it, so we would subtract it. We know the mass of mass 2, it's 0.93 kilograms. And we know from that first bit what the acceleration is, right, because the acceleration is of the system, which means that's the same acceleration of each individual mass as well. So we can use that 1.1, or we can go back and use our actual non-rounded value of 1.064 meters per second squared for acceleration, right? And remember, what we're trying to solve for here is force of tension. So what we need to do is just add the force of friction to both sides, and we get force of tension on its own. So force of tension now will equal, now this 0.93 times the 1.064 meters per second gives us a value of 0.990 newtons. And now we're going to add force of friction, right? Because we're adding this to both sides. If we do that, remember your force of friction is the coefficient of friction, mu, multiplied by your normal force. Okay? Now, we had the coefficient of friction, right? It was that 0.16. And our normal force is the same as our opposite force of gravity, right? Because technically you still have force of gravity here and normal force here, but we're not, they're balanced forces. And your force of gravity would equal mass times your acceleration due to gravity, mg. So really it's just the mass of m2, which is 0.93 kilograms, multiplied by your g value, we're assuming we're on Earth, 9.81 meters per second squared. Okay, and like I said, that's being added to that original, MA value there, right? So it's that 0.990 newtons, and then you're adding your force of friction, which is calculated by your coefficient, 0.16, times your mass, 0.93, times your 9.81 meters per second squared. Okay, so then that gives you a value of 2.45 newtons, and with 2 figs we would put that up to 2.5. So the force of tension in the rope is 2.5 newtons. Okay, now like I said, you can choose your mass here. So what you could have done is dealt with m1, right? But then what would have happened is that your F net would have involved 3 forces, where it would have been Fa minus Ft minus Ff equals, and then this mass would have been 1.5, but the acceleration would have stayed the same at that 1.064, right? And you would have had to calculate your force of friction for that mass. You would have had to include that applied force in it, and then being able to solve your force of tension. You get the same answer, okay? I just don't necessarily want to waste more time in the video and going over that, okay? But if you would like to see it, just let me know and I'll show it to you. Okay, so that's that example done. All right, solutions, here we go. So in this one, there's no rope connecting them. What we have instead is just that contact force that we talked about, okay? So in this case, things are just being pushed against each other, and even when something's pushing against each other directly, we have that kind of contact force, and one's pushing against the other, and the other in the same way going back, okay? So in this one, we've got a 5 kilogram and a 10 kilogram box are touching, and we'll do those respectively. I know this one looks larger, but let's just say it's got a lower density. Okay, so that's first one is 5 kilograms, the second one is 10 kilograms. Okay, they're actually touching each other. A 45 Newton horizontal force is being applied to the 5 kilogram box in order to accelerate both boxes across the floor. The coefficient of kinetic friction is 0.200. Determine the acceleration, right, of the system as well as the contact force. Okay, so similar idea as the last one. Okay, so with this one, same problem number 3, right? Again, you've got your free body diagram. You have MA, and then you've got MB there, and you've got an applied force acting on it, and then of course you've got a force of friction kind of pulling against it, right, as the net force, okay? And then what's happening is in between here, you've got a contact force going one way as well as, right, so like the mass of A is acting on the mass of B in this direction, but the mass of B is pushing back in that direction with that same force, okay? Now, if we just think of this as an overall system, right, so that's kind of all the little bits and parts all together. If we think of it as an overall system, well, what you have there is a single mass, right? That's the sum of the two masses, where you have that applied force, and I guess I should have drawn it like this, right? Pushing it in this direction, and a force of friction holding it back, okay? And again, if we're looking for the acceleration, F net is equal to mass times acceleration. Now our F net in this system is our applied force minus our force of friction is equal to our two masses, right? The mass of the system multiplied by the acceleration of the system, okay? Our applied force was given to us as 45 newtons. Our force of friction we can calculate, right? So remember that that's mu times Fn. We can add our two masses, right? 5 kilograms and 10 kilograms. So altogether we get 15 kilograms, and we're solving for A, right? So the only other bit of work we still need to do here is actually calculating that normal force, right, for force of friction. But again, it's that same idea where we're not experiencing any sort of change in the vertical. So this force of gravity pulling down is going to be the same as the normal force, where they would just cancel each other out anyway, right? They're balanced. So our normal force would just equal that mass times gravity. So again, this is our 45 newtons minus our coefficient, which was given to us as 0.200, multiplied by our normal force, which is the same as our force of gravity. So it's the mass, which was the sum of the two masses, so 15 kilograms, multiplied by our 9.81 meters per second squared, and that's equal to our 15 kilograms times the acceleration. Okay, so this we can calculate, right? The 0.2 times 15 times 9.81, right? So we have 45 newtons of the applied force, 29.43 newtons of force of friction, which is equal to our 15 kilograms multiplied by our acceleration. So we can take the difference there and say, okay, 45 minus 29.43, that's 15.57 newtons is equal to the 15 kilograms times the acceleration, and then it's just a division there, right? So 15.57 divided by 15, and you get an acceleration of 1.038 meters per second squared. And we get, I think, 3 sig figs for this question. So we'll put this as 1.04. Right, so the acceleration of the system is 1.04 meters per second squared. So now what we need to find is the contact force. Okay, so if we're looking for the contact force, we need to look at a specific mass. Okay, so we can either look at mass of A, or we can look at mass A, or we can look at mass B. Okay, and again, either will work here. So if I look at, again, the overall system, right? So I should actually redraw that again. So you've got this applied force, you've got mass A here, and mass B here, okay? Looking at them individually, what's happening to mass A is that you've got an applied force pushing it this way, right? So this is mass A. You've got the force of friction acting, right, against it, but you've also got that contact force with mass B, right? So it would involve 3 forces. Now, the other thing we can do is look at mass B, right, over here. So if we look at mass B, you've got the applied force, right? And you've got, actually, sorry, you don't have the applied force. The applied force is not being pushed onto mass B. The thing that's pushing mass B is your contact force, and it's only friction pulling it back. Okay? I'm going to redraw that. Make that clearer. Okay, so again, in that situation, right, there's this mass here and this mass here. Okay? Force is being applied to mass A. Okay? Then you've got contact force going from A to B, but then also from B to A, right? And then you've got force of friction acting against both masses here, right? So again, if you're looking at just mass A by itself, right, there's an applied force pushing it to the right, there's a contact force pushing it to the left, as well as a force of tension pushing it to the left, and that should be a straight line, not a diagonal. Okay, so you got your contact force, and again, your force of tension. However, with just looking at mass B, the forces acting directly on mass B are this contact force pushing it to the right, and a force of friction pushing it to the left. So once again, looking at mass B involves less forces, okay? So that would be the simpler one to deal with, where your F net, being mass times acceleration, would simply be your contact force minus your force of friction, which is equal to your mass, and that one was 10 kilograms, multiplied by the acceleration, which we calculated as 1.038 meters per second squared, right? And then again, you could figure out your force of friction, right? Mu times Fn, this ends up just being 10.38 newtons. So we had the coefficient of friction given to us as 0.2, and our normal force again would have just been the same as our force of gravity, which is our mass of 10 kilograms multiplied by our 9.81 meters per second squared, and that's equal to that 10.38 newtons there. Okay, so ultimately what you get is you can calculate this and bring it over to the other side. So your contact force is that 10.38 newtons plus this value of the force of friction, which ends up being 19.62 newtons, which means your contact force is a nice even 30 newtons. Okay? Again, this works the exact same way if we had looked at mass of A, right? And I'm not going to do the full thing, but I am just going to kind of show you how with this one, using the mass of A, your net force is going to equal your force applied minus your contact force minus your force of tension, which is equal to the 5 kilogram multiplied by that acceleration of 1.038, right, meters per second squared. And if you do this one, right, this ends up being a value of 5.19 newtons. We already had the applied force was the no, that was a different question. This was the 45 newtons. And this should have said force of friction, not force of tension. Okay, so this was the 45 newtons minus the contact force which you're trying to find, and your force of friction here would have again just been your coefficient of friction of your 0.2 times your 5 kilograms times your 9.81, which ends up actually being a value of just 9.81, because 0.2 times 5 is 10, or 1, it's late, right? So to get your force of your contact force here, you can bring that to the other side so it becomes positive. And what you get is this 45 minus 9.81 minus the 5.19, and lo and behold, you get your 30 newtons again. Okay, so it can work with either mass. You just have to really be, looking at your question carefully as to what forces are actually acting on which mass individually. Okay. All right, so we'll do our last problem here, something that's a little bit different, where we don't have them lying on a horizontal surface, but instead masses that are hanging, okay? And even hanging masses can be interpreted as you could kind of stretch them out, but it's another interesting one to look at, and you look at these a lot more as well in Physics 12. So with this one, you've got these two masses that are hanging from a frictionless pulley, so we'll assume there's no friction slowing things down as the rope pulls through the pulley, and they're released at rest. Okay, find the acceleration of the system and the tension in the string. Okay, so they're not moving to begin with, you just release them, and then what we're trying to figure is after we release them, and they're just hanging, right, what will the acceleration of the system be? Okay, and then what's actually the tension of the string itself. Okay, so let's look at this last one together. So with this one, right, what you've got is, again, there was this mass of 6 kilograms here attached to this pulley, and you had this mass here of 4 kilograms. Okay, now a little bit of just common sense will tell you if you've got two weights, right, hanging over a pulley and you let them go, gravity's going to have a stronger effect on the larger mass. So what's going to happen is when we let these 6 kilogram and 4 kilogram weights go, since 6 kilograms is larger, overall the motion is going to go this direction, right? So we can consider any motion in this direction positive, let's say. Okay, so if we look at that, now we start needing to think about, well, what forces are acting on these masses? Well, gravity is pulling on this force here, and gravity is pulling on this force here, and there's a force of tension in a rope, right, that's pulling this way, and there's a force of tension in a rope pulling this way, right? Now, if we kind of like took these masses and then stretched them out and looked at them as like a straight line, okay, you've got your 6 kilogram mass here, right, which was being pulled right this way, force of gravity 1. Then there was this force of tension here, connecting it to this 4 kilogram mass that also had a force of tension pulling in that direction. And again, if we think about straightening that out, then you had your force of gravity 2 happening over here. Right? Again, if you look at this as a system, what you notice is that it's your two force of gravities that are acting against each other to give the net force, because these guys are going to cancel each other out, right? Because there's the same force of tension acting in opposite directions, right? So in this case, your F net equaling mass times acceleration, well, since we said going this way is considered positive, it's our Fg1 minus our Fg2 is equal to the mass of the system, right? So m1 plus m2 times the acceleration of the system. Okay, so again, you can even think of this way, right? This is going to pull down, this is going to pull down, these are going to pull in towards each other, right? So they cancel out. So that force of gravity here is your mass which is your 6 kilograms, multiplied by your 9.81 meters per second squared. I'm going to give myself more space here. Right, so you've got your 6 kilograms multiplied by your 9.81 meters per second squared minus your 4 kilograms multiplied by your 9.81 meters per second squared is equal to the sum of your masses, so 6 plus 4, which is 10, times 10 kilograms times your acceleration. Right? Calculate this. You get a value of 58.86 newtons. Right, calculate this. You get a value of 39.24 newtons, and that's equal to your 10 kilograms multiplied by your acceleration. Subtract them to get your net force. 19.62 newtons is equal to your 10 kilograms times your acceleration. Divide both sides by 10. You get 1.962 meters per second squared as your acceleration, but with only 2 sig figs, we would round this to a nice even 2.0 meters per second squared. All right, there's your acceleration. And then finally, force of tension in the string. So again, now that it's just force of tension, we can't use the system because they cancel each other out, but we can just look at a single mass. We can either just look at the 6 kilogram mass, where you've got the force of gravity pulling down and the force of tension pulling back, but acting only on a single mass. Right? Or you can look at mass number 2, where again, in this case, force of tension is moving in the positive direction, force of gravity is pulling it down, and it's only acting on that single mass, right? Choice is yours. In this case, it really doesn't matter. Both are just as simple, right? And you get the same value. But if we, let's say, take a look at, mass number 1, okay, so let's say we were dealing with M1 here, right? Then what's happening is our, again, F net is equal to mass times acceleration. And what's happening is that you've got your force of gravity pulling down, but that's in a positive direction, minus your force of tension is equal to the mass, which is just the 6 kilograms, multiplied by the acceleration, which we know the acceleration of a single mass is the same as the acceleration of the system. So we'll use that we'll use the non-rounded 1.962 meters per second squared as that acceleration. We already calculated that force of gravity, right? But we can just do it again, right? It's the mass, which is our 6 kilograms, multiplied by our 9.81 meters per second squared. We're trying to find the force of tension, and this mass times acceleration, 6 times the 1.962, gives us a value of 11.772 newtons. Right, so again, what we want is this force of tension. So since it's negative here, I'll bring it to the other side and then bring this 11.772 newtons over, right? So 6 times 9.81. So this was 58.86 newtons minus that 11.772 newtons. That's going to equal my positive force of tension. And that gives us a value of 47 newtons, pretty much bang on. I think it's like 47, it's 47.088 newtons, but again, it's only 2 sig figs, so we're just going to use 47. Right? And I mean, feel free to try it with the other mass, but you do get the same answer of 47 newtons as the force of tension indicator. Okay? So, right, I've given you lots of examples there, right? So again, just noting when you're solving for the acceleration of the system, right, you have to consider the total mass of the system, whereas when you're just looking for finding a tension in a rope, you just consider one mass, pick which one you want to use, okay? So you've got some practice problems to work on here with this. Solutions, again, always provided. I know that was a longer one, but I just wanted to give you a few different, examples of what was happening, okay? So just again, email me with any questions that come up with that worksheet, and we'll kind of go from there.